Hey everyone, welcome back in the office, and we got another fun video today. I'm going to start talking about a couple of different kinds of circuits. We talked a lot about the components that can make up the circuits, but let's start talking about one of the more simple circuits, probably the most simple circuit. Without this, it's kind of hard to understand why a lot of the other circuits work. For example, the audio filters. If we don't understand the circuit principles, it's really hard to understand what's going on in the background. So this one's called a series circuit. Now, series circuit is whenever two components follow each other in a series inside a circuit. So as resistors, I'll use these huge fat resistors just so that you can see them. You probably wouldn't be using any resistors near this size, but this is an example of a series configuration where the electricity would have to go through both resistors before it makes its way back to the power supply. Now, usually we'll see this on a breadboard or on a circuit, but series circuits are one of the easiest ones to be able to manipulate and calculate the response of that circuit. Something that we need to understand with resistors that are in series, each resistor has a certain amount of material that causes resistance to the electrons flowing through it. So if a certain length of that material has a certain amount of resistance, if we stick another identical length of that material following it, it's as if we just had two lengths of those materials. If they're two identical, then it's just double the amount of material that it has to go through. If one of them is smaller than the other, we still find it by just looking at the total sum of all the material that goes through it. Sum is a math process, it's addition. So if we want to find out the total amount of resistance in a series circuit, we just add the two individual resistances together. There's some shortcuts, like if they are exactly the same size, sometimes that'll happen on a what they call a voltage divider, which we'll see in a second, but sometimes there are uses of having a whole bunch of identical resistors all lined up. We can simply multiply by the amount of resistance, multiply that by the number of resistors, and it'll give us the total. If they're individually different sizes, then we can just add them all up. The total amount of resistance paired with the total amount of voltage would give us a total amount of current in the circuit, as followed by Ohm's law. So the amount of current I equals the total amount of voltage divided by R, which is the total, or in this case in a series circuit, the sum of all of the resistors together, the addition. If we want to find out how much voltage is being dropped by each one of the resistors individually, we simply say, well, if there's electricity flowing, that's the current, it must be flowing through all of the resistors. It can't really back up. There's no other path for it to go. So if we've already found the total current in a series circuit, that must be the total amount of current that's passing through all of the components. So that's a constant. It's a number that doesn't change. If we read the front of it, in this case, it's actually printed on it. You can see a couple of different resistor values. Sometimes we have to read the color codes on it. But we have a fixed amount of resistance. Now, if we take that fixed amount of resistance along with the current, we would be able to figure out the amount of voltage that's being dropped by each one of them. Now, if we have a 9-volt supply, like a 9-volt battery supplying this circuit, each one of these resistors is not going to get 9 volts by itself. If they're identical sizes, then each one of them is getting half of the voltage. If they're not exactly the same size, we should be able to figure out how much voltage each one is getting based on the amount of current multiplied by the amount of resistance of that individual resistor. If we put two of these together, sometimes as many as 3, but 2 is more common. If we put two resistors together in a circuit in series and watch as each one drops a differing amount of voltage, we would say that that voltage is divided between the two resistors, or a voltage divider. That's what we call that kind of circuit. So here I have built a voltage divider on a breadboard. We have a 6-volt supply coming in, and we have a 2-resistor series circuit. Now, each one of these resistors is rated at 22 ohms. Be careful of resistance, just making your own voltage divider, because we can very easily overload a power supply if the resistors that we've chosen are too small of a value. If you're experimenting with this kind of stuff at home, we usually try to use resistors that are up in the kilo ohms, the thousands of ohms range. That keeps the current down at such a safe level that any resistors that you choose would be appropriate. So as long as they're in the thousands, the kilos, or the tens of thousands range, then you're just fine. Now these ones, I'm trying to use bigger ones just to kind of get the visual effect. But these ones can have very, very low resistance values. So if you be really careful if you're seeing resistors that look like this, sometimes they can have resistances down in the fractions of ohms, allowing through way too much current, and that can severely damage batteries, power supplies. It can also be a real safety issue if you're holding a power supply or holding a battery and you've started overloading it, it can catch on fire and sometimes even explode. So be really careful with low resistance values. But these ones, I've chosen ones that are going to be well below the maximum range of the power supply. Now these ones on the breadboard are 22 ohms. Now they're both identical, so that means that the 22 for one of them plus the 22 for the other one gives us 44 ohms. 44 ohms and a 6-volt power supply. Now, in the case of a voltage divider, the keyword there is voltage. Yes, we're interested in current, but in the case of a voltage divider, far less interested in the amount of current than the amount of voltage. So that's why usually in a voltage divider application, we're going to see very high values of resistance, because then the current value is kept very low and never going to be a risk to the components in the circuit, the power supplies and things like that. But if we use values that are too high, sometimes we start seeing differences, significant differences, just by taking measurements. And I'll explain why in a little bit. So I'm going to take my multimeter, my voltmeter here, and I'm going to connect it across the two leads of the resistors. And then we're going to see what happens when we have the voltage for those resistors set up in series. If they are exactly the same and the exact same current is going through them, then mathematically we would expect exactly the same voltage. And if there's only two components, they share exactly the same voltage, that should be half the voltage in the circuit. So we're going to check that out and see if we do in fact get half of the voltage in the circuit for each one of these resistors. So first, let's measure the entire power supply, which means we want to make a connection with the ground lead, the common lead, all the way at the negative side, and the positive lead all the way at the positive side. And we can see from the voltmeter, it's a little bit shy of the 6 volts, 5.76 volts. Now the power supplies, they might fluctuate a little bit, especially as the resistors, if they're low value, start to heat up just a little bit. If I put the back of my hand on here, I can feel they are slightly warm, but again, I use 22 ohm resistors. That's a really low value. I wouldn't recommend using really low resistor values when you're testing voltage dividers. But then now let's test each one of these individually. Common lead on the lower voltage side, so right next to where it connects to the ground of the power supply, and the positive lead up at the other end. 2.8, we'll let it kind of settle there. We'll call that 2.82 volts. And let's test the other one, just to see how closely it matches. Very, very close. That's exactly what we expected, since these are both 22 ohm resistors. Now, what I mentioned with connecting a voltmeter to it, the voltmeter actually allows a little path for electricity, but it's not very much. It doesn't allow very much electricity through it. That means we would be able to, we call that a high resistance circuit, because there's not much current. They're inverses of each other. So if it's not allowing very much current through it, then there's really not much difference. The circuit doesn't see much difference between this low resistance circuit and when another very high resistance is stuck on alongside next to it. Think about this, we're kind of bypassing this resistor with a little bit of electricity. A couple of electrons are going through the meter instead of going through the resistor. That's what we call a load, when we've connected a device to another electricity supplying source. It's a load device on it. So we've loaded up slightly, but not really enough to make any difference here. Now I'm going to switch out these resistors with ones that are not the same size. They're disproportionate sizes, so we can do a little bit of calculation and see if it still matches what we expect. So now I've switched out these two resistors. Instead of being identical 22 ohms, they're much higher resistance now. We have a 6.8 kilo or 6,800 ohm, followed by a 2 kilo or a 2,000 ohm resistor. That means we have 8.8K or 8,800 ohms. If we take our 6 volts and divide by 8,800 or 8,800, we end up with a much smaller amount of current. the amount of current that we end up with is less than a milliamp. It's only about 680, 682 microamps, about roughly 7/10 of a milliamp. That's far less current than we had originally, 22 versus the up in the thousands, 6.8 thousand and 2,000. If I touch these lightly, I'm not going to really feel anything heating up on these ones because the amount of electricity flowing through them and their power dissipation then is much lower. But since this one is 2K versus 6.8K, we think about the ratio there. Now, if they were identical, the same size, they'd have the same size voltage. Now, in the case of a series circuit, we thought about, okay, voltage. Voltage was multiplying, I times R. Now, the current going through both is still the same. Granted, it's a lot less, but it's still the same current through this one as through this one. So that number is the same. That means it must be up to the resistor differences to determine the voltage differences. If it's multiplied, V equals I times R, the bigger resistor is going to have a bigger effect in the multiplication. So therefore, we're going to get a bigger voltage. Whichever of the resistors is a larger value, that's the larger voltage that we're going to see as well. The amount by which it's larger, if you think about 6.8 versus 2, that ratio isn't super easy, but let's do some rounding just to kind of get an idea. Let's say the 6.8 was only a 6. 6,000 versus 2,000. Well, that's exactly 3 times more. That means I would expect to see 3 times more voltage. So it's going to follow the ratios. Let's see if logically that makes sense. Now we have 6-volt power supply, 2K versus 6.8K. I'm going to do a little bit of math here and see if I took my amount of current that I calculated and multiplied it by the 2,000, so current times the resistance equals the voltage, I get 1.36. Let's go ahead and test and see how close that is to 1.36 volts. Very close. Why is it not exactly 1.36? Well, first of all, resistors have a tolerance. They're not going to be exact, but that's going to be pretty close. Let's test the other one now and see what we get. 1.36 versus 4.77. Okay, was it roughly, again, that 6 was really rounded. If we called 6.8, we rounded it down to 6. That's a huge amount of rounding. But if 2, 4, 6 volts, we're going to end up with a ratio that would say that other resistors should be significantly larger than 2 by somewhere around the 2 to 3 times larger. Okay, 1.36 versus 4.8, I'd call that right in that reasonable guess range. We'll let the calculator do the detail work down to a couple of decimal places, but it makes sense. 6.8 versus 2K. Now, if we add those two numbers together, we had I'm writing these down on the calculator, so don't forget them. 1.39 volts, 1.39 plus the other resistor, 4.77. We get exactly 6.16 volts. Let's measure our entire power supply and see what we get. 6.19 instead of 6.16, very, very close. The multimeter is making very slight differences in the circuit, but you'll notice that we actually got a lot more voltage in this measurement than we did in the last circuit with the 22 ohms. I'm using the same power supply. Nothing's different except less current. If I pull more current, which means less resistance, I'm going to draw down the voltage of the supply. It's exactly what I saw. Now also, those two resistors together, the resistances added up to get the total resistance, but the voltages also added up to get the total voltage. And that's the case with any voltage divider. We add up the two individual voltages that we get, and that's going to give us the total voltage in that circuit. So this really simple demonstration of voltages in series, a voltage divider circuit, gives us kind of the base work for looking at a whole bunch of other circuits. And one of the components that I'm going to talk about sometime really soon is the potentiometer. It's kind of hard to discuss that one without knowing a little bit about voltage dividers in series circuits first, because one of the main principles of a potentiometer is acting as a voltage divider. A lot of different types of what they call analog circuits and a lot of industrial cases as well, use voltage dividers to be able to get a reference voltage. Now, important thing, we do not drive loads. We do not drive machinery using a voltage divider. We usually reserve that for reference signals. So if we want to send information about something, then we can use a voltage divider. If we want to limit the amount of current that's being sent to something in order to drive a device, we usually have to turn to something other than a voltage divider circuit, because the amount of current that bypasses those resistors, like that voltmeter was doing, the amount of current that bypasses it drastically affects the calculations. So you can see that if we were trying to drive something that used a varying amount of current, we really don't have any consistent calculations that we can use. And that makes a very dangerous scenario when we really can't trust things being similar in a circuit or always staying the same, consistency. So we tend to only use voltage dividers when a very low current reference signal is desired, not driving a load device. Thanks for watching. I know this video has been a little bit longer than most of them, but the series circuit is extremely important in an understanding of electronic circuits. It's one of the absolute base principles of how circuits work. The parallel circuit is another one coming up soon. But thanks for watching. Hope you had an interesting time learning a little bit more about these circuits, and stay tuned. We're going to talk about a lot more.